How does your smartphone knows exactly where you are? The answer lies 12,000 miles over your head, in an orbital satellite that keeps time to the beat of an atomic clock, powered by quantum mechanics. Let's break that down. First of all, why is it so important to know what time is it on a satellite? Well, location is what we're concerned about. The first thing your phone needs to determine is how far it is from a satellite. Each satellite constantly broadcasting a radio signal. It travels from space to your phone at the speed of light. The phone records the signal arrival time. Uses it to calculate the distance to the satellite. Using the simple formula distance equals c times time, where c the speed of light and time is how long the signal travels. But there was a problem. Light is incredibly fast. If we were only able to calculate time to the nearest second, every location on Earth and far beyond, which seems to able the same distance from the satellite. So in order to calculate the distance to within a few dozen feet, we need the best clock ever invented, atomic clocks, some of which are so precise they would not gain or lose a second, even if they ran for the next 300 million years. Atomic clocks work because of quantum physics. All clocks must have a constant frequency. In other words, a clock must carry out some repetitive action, arc of equivalent increments of time, as a grandfather clock relies on the constant swinging back and forth of pendulum under gravity. Tick-tock of an atomic clock, maintained by the transmission between two energy levels of an atom. This is where quantum physics comes into play. Quantum mechanics says the atom carry energy. They can't take on just any arbitrary amount. Instead, atomic energy is constrained to a precise set of levels. We call this quantum. Simple analogy: think about driving a car to a freeway. You increase your speed. Normally continuously go from say 20 miles per hour up to 70 miles per hour. Now, if you had a quantum atomic car, you wouldn't accelerate in a linear fashion. Instead, you would continuously transition from one speed to the next. From an atom, when a transition occurs from one energy level to another, quantum mechanics say the energy difference is equal to characteristic frequency multiplied by a constant, where the change in energy is equal to a number called the Planck's constant times the frequency. Characteristic frequency is what we need to make our clock. GPS satellite rely on cesium and rubidium atomic as a frequency standard. In case of cesium-133, characteristic clock frequency 919263177 Hz. That's 9 billion cycle per second. That's a really fast clock. No matter how skilled a clockmaker may be, the pendulum wind-up mechanism and quartz crystal at the slightly different frequency. Every cesium-133 atom in the universe played at the same exact frequency. Thanks to the atomic clock, get a time reading accurate to within 1 billionth of a second, a very precise measurement of the distance from the satellite. Let's ignore the fact that you are almost definitely on Earth. Now know that you are a fixed distance from the satellite. You are somewhere on the surface of the sphere, centered around the satellite, distance from a second satellite, and you get another overlapping sphere. Keep doing that, and with just a 4 measurement. Little correction using Einstein theory. Pinpoint your location to exactly one point in space. So that's all at stake. Multi-billion-dollar network of satellites, latent cesium atom, quantum mechanics, relativity, smartphone, and you. How does your smartphone knows exactly where you are? The answer lies 12,000 miles over your head, in an orbital satellite that keeps time to the beat of